Bismillah ar-Rahman ar-Rahim. So this is the fourth lecture of chapter 1. We are الأربعاء 20 سبتمبر 23 Wednesday 20th September 23 in Malaysia. And we have already seen in the three previous lectures the problem, the method, how to apply it, and then how we implement it in an algorithm. Now we focus on the final two sections, how to criticize or critics to this method, some critics to these methods, edge cases, and then in the next section, an overview of a short overview on the other methods. So let's begin with section 1.5, method analysis. The pros and the cons. That is the advantages and disadvantages of the method. The pros and cons. Let's first start with the pros. So first thing to observe that is that the method always converges, always. That is the sequence of XRI, the false points, from the first iteration to the nth iteration, where we stop the loop, where we stop the iterations, always converge to the solution, X star. And all the XRI, Ri, all the elements of the sequence are bracketed. Bracketed, I mean, in the interval AB that contains the solution. That's why the method is called a bracketed method. So this is the first advantage. And as we will see later, there are methods that diverge, that will not necessarily tend to the exact solution. The second pro is that it's easy to learn. It's very easy to learn. It's a pedagogical method. It's easy to learn. And also to apply using a calculator, and also easy to implement. It's an old method. It has about 11 centuries. It has survived all these centuries because it's of easiness. It's very easy to apply, to learn, and to implement. That's the two pros, the two advantages of this method. The cons. The first con is that we need the interval AB. The method does not give us the interval. It's an input to the method. We must first know the interval AB that contains the solution. And we have seen how to remedy this problem by drawing. So we can find a solution to this problem by drawing the function that represent the equation, function fx. And then visually we find the interval that contains the solution. Or if there are several solutions, we can choose the interval we are interested in. So it's not a big deal here, but it is still a disadvantage. You cannot apply the method directly. You need the interval. The second disadvantage is that the method could be very slow in some cases, in edge cases. In general, it works fine, but there are cases where it behaves slowly. Which cases? The case where the function, I draw it here quickly, where the function, this is the curve of the function, this is the interval, let's say A, and let's say B. So the function at one endpoint varies slowly, and then at the other end it varies, increases abruptly, or vice versa. Important thing is that the change at the end points is significantly different. Then it will take time or iterations, not time, iterations, the number of iterations to the first chord to reach the solution. A good example is x power 10 minus 1 equals 0. Find x in the interval 0, 1.3. Using the algorithm I have explained in the previous section, and we will test it in the next practicals. I have found about method converges in about 33, not in about, in 33 iterations. Exactly in 33 iterations, it reaches a solution with a maximum error of 0.05% and with a tolerance of 100 epsilon in 33 iterations. And here also one research worker, a mathematician, recently, the method has is been known is known. I mean, since the 9th century. But this modification is recent, in the 50s, the 1950s, and is called Illinois Modification in the University of Illinois. So a way to overcome. So here also there is a solution to this problem. To overcome this problem or this advantage, there is a modification called Illinois Modification that makes the number of iteration drop significantly. In 7-8 iterations, we can reach a solution. How we do that, we will see that later in this section, but later. So these are the main pros and cons, and as we can see, even the disadvantages, we can find a solution to reduce their bad effect on the method. So overall, the method is really very nice and useful in this topic. Second section, we will see, in this section, we will see what we call edge cases or special cases, where the method behaves not as it usually behaves. Edge cases. There are 3 edge cases. The first is when the solution is 0. When xf star equals 0. Let's see my note. Is logarithm Neperian of 1 minus x plus x squared equals 0. Find x in the interval minus 1, 0.5. Now we can easily check that for x equals 0, the function equals 0. So it's a solution. What happens here? When you observe each iteration, using, of course, using a program, not with a calculator. Even with calculator, the first iterations. But it's better to study these cases, these edge cases, with an algorithm. We'll come back to these edge cases in the practicals. But let's observe the problem here in this edge case. What is the problem here? Why it is an edge case? So we have seen that EA, I've studied that EAI assesses the progress of the element of the sequence xi. That's the xi. The false point from their progress. So it decreases, and when it reaches a certain amount, we stop the loop, we stop the iterations. But in this edge case, the error will never decrease. In the opposite, it will increase. So in this case, the first iterations, well, we will see that the absolute error, the approximative absolute error, which measures the difference between the current and the previous, this absolute error measures here -1, measures the difference between the current false point and the previous false point. This absolute error and the current false point in this edge case have the same magnitude, have the same magnitude. What does that mean? In our case, we take, in this example, if we take EAI divided by over XRI, we find almost -1.4. For I equal 2, 3, etc. For I equal 1, of course, it's 100%. But for the subsequent iterations, it's almost constant, because this value and this value have almost the same magnitude, the same value, the same number. Very small, but almost the same. And that implies that the relative approximative relative error, which is this ratio, by 100%. So it's about 1 by 100%. And it becomes -40%. It increases, it's very large. And it becomes even larger when XR tends to 0. The false point decreases, but also the error decreases. The error between the false points decreases in the same amount, in the same magnitude. So you get the relative error very big. And so it is useless to assess the progress. It is no more a break condition. So in this case, in this special case, EAI, absolute value, less than max EA is no more a break condition. So how we can assess that XR is close to the solution? We use the first break condition. So only the first break condition namely the absolute value of FRI, the image of the current force point, is less than or equal the tolerance. This is the break condition. This is the only break condition in this edge case. This is the only break condition in this case, in this edge case. So it's not then a big deal because you have two break conditions. If the second doesn't work, the first will. But it's important to know that if you discover that in your results that the error is very large, it's because the absolute error at the current iteration and the force point at the current iteration have very close values, have the same magnitude. They decrease, but they decrease with the same numbers, the same values. And this is just an example. In any example, when you have the solution is zero, you will observe this behavior. The second edge case is when the method oscillates. We have seen in the table, in the section where we applied the method with the function exponential minus x equals 0, we have seen that the method does not oscillate its interval or its intervals. At each iteration, we catch the solution at the left, then the subsequent intervals will be also at the left. But there are cases where the method oscillates, sometimes at the left, sometimes at the right, but for few iterations only. This is also an edge case. This is a special case. Let's observe that through an example. So let's draw. It's not this case, it's another case, another example where the method change. Oh, this is the first, this is the second. And let's draw our curve here like that. This is the interval AB. This is the curve of F. And what you observe here that the root is an inflection point. The curvature has changed at the solution. So this case happens when XR star, the root, the exact root, the intersection of the curve with the x-axis, is an inflection point. An inflection point means the function or the curve changes its curvature at this point. So this is the case where it oscillates, and it oscillates only in few iterations in the vicinity of XL. And then it catches at the left or at the right, depending of the function. So in this example, let's draw the first chord of Abou Kamel. Would be, I beg your pardon, It should be here. This is the first point. We started with this interval. Now you can see we are at the left. Then the image, this is X R1, this is FR1, FR1. And the second chord will be like this. This is XR2, and the image should be here. This is FR2. And we can observe that the interval now is at the right. The interval is at the right. It was at the left, now it is at the right. The third interval is this one. And we can also observe that the image is here. It was here positive, and now it changes its sign. It is now negative. It changes the side of the curve. It was on this side, and it jumps to this side. So the method can oscillate when we have the solution, the root, the exact root is an inflection point in the vicinity of the root. So we should not say that the method will never oscillate. It never oscillate in the majority of cases, but there are cases where it can oscillate. And this has, of course, no consequences on the convergence of the method. So let's move to the third edge case. The third edge case is the case where the function is very slow. So here we will see case where the method is slow, and we will see also the remedy to this problem. Illinois Modification by Snyder, S.N. Snyder, in 1951. It is known as the Illinois Modification. It should be the Snyder modification, but yeah, it is known as in bibliography. It is known as Illinois Modification, and it's not the only modification. There are others, 2 or 3 others, but this one is the simplest and the most known because it's very simple and give a drastic change, drastic improvement to the method, and it's very easy, very simple. We will see that now. So let's see it through an example, graphically, through an example. These are the axes, and let's draw the curve between this is 1 and 0, and have here our method. So here it increases abruptly, and here it increases slowly. here is minus 1. This is our function. The function is x power 10 minus 1 equals 0. Find x in 0, 1.3. Now it starts here. This is b, 1.3, and this is a 0. So when we start when we apply graphically the method, as usual. We draw chord joining the images at the endpoints, and the intersection is our force point. This is XR1, and then its image comes here, and then we do the second, and its image comes here. So as usual, we apply the method as usual, FR1, FR2. So at least the two first iterations are the same. But what we observe that FR1 and FR2 are on the same side of the curve. So for the next interval, should be this one. And it should join these two, the FR2 and the image of B, the images of the endpoints of our interval, normally like that. But what Snyder has proposed, in the case that the previous image is in the same side as the current image, not to join the two images, but to decrease the image of the other endpoint to its half. So to join our chord with this point, which is equal FB over 2, or FU, upper bound, of our second interval divided by 2. It's the same because the interval has not changed its endpoints. The method does not change the endpoints. It changes the image of one of the endpoints. In this case, the upper bound. Its image becomes its half. And we draw, let's draw it another color, and we draw like this. Now it should be here. Our force point should be here. It has moved here. It accelerates the process. And our solution will be here. And we repeat again, as usual, the image of the endpoints. This is our new interval. And we check FR3 is still on the same side, Only when it is on the same side, we apply the rule to half the image of the other endpoint. Otherwise, we do not. We keep the original image. So the image is here. We half it again here, and we get even closer. As you can see in the figure, it gets very rapidly to the solution. This is the solution. solution is XR star equal 1. So it gets very close in few iterations. So let's summarize this in simple rule. Let's write it in simple rule, and we will see how to modify our algorithm. The algorithm we have studied in the previous section, we will implement it in the practicals with MATLAB, with function, and script. We test it. And we'll come to the edge cases and we will test them. And we will see how to implement this modification. So let's see it here, but its implementation, we will see it in the practicals. It's very simple, very simple. And that's why it makes it very useful modification. If it was complicated, it will make the iteration slow, etc. It's very easy, very simple. So what does the rule? As I explained it here graphically, I explain it or formulate it with equations, symbolically. So if, mathematically, I mean analytically, so if f Ri and the previous, this is the images are carried by the curve. If FRI, the current image of the false point, and the previous, and the image of the previous false point are on the same side of the curve, they have the same sign of the curve, then we have two cases. Here we work at the right, but there could be also another case where the curve changes and we work at the left. So when we have at the right, what we do? The interval, as usual, the next interval, x left, I plus 1, and xu, I plus 1, equal, as let me check my notes, should be at the right. Okay. As usual, the upper will not change. So xu, I. But the lower will become xr of the current. So the next lower bound is the current false point. Is the current false point. Is the current false point. But the upper will not change. Okay. So this is as usual, nothing here new. But the image of the upper bound, the next image of the upper bound will not be fu of the current point. Will not be fu I. Will not be fu I. Will not be fu I, as we used to do in the normal Abou Kamel method. But instead, it's half. Not fu, but instead it's half. And this is what we have done here. We took the half. We took again the half. So whenever the image of the current false point, and the image of the previous false point are on the same side, we simply subdivide the image of the upper endpoint, xu. The interval will not change, only the image. We simply divide it by 2. And at the left, same. So the interval xl, I plus 1, xu upper plus 1. Here, the upper bound will change, but the lower will stay the same. This is usual method of Abou, but here the lower, the side that does not change, the endpoint that does not change, I mean FL, for the next iteration, is not the same, but we have it. So again, at the right, the lower endpoint will change, and the image of the upper endpoint will be halved. Upper. And here the upper endpoint will change, but the image of the lower endpoint will be halved. This is the modification of Snyder. Very simple modification, but has a dramatic change. In our case, in this equation, the number of iterations the consequence, when we apply this method, the number of iterations drops from 33 to only 8, I think. Yeah, to 8 iterations, making the method 4 times faster. So it is really a very good modification to our method. And that's it for this section. Let's move to the next section. This is, I think, number 9.